All right, hi everybody. My name is Brendan Mangino. I'm from a project engineer from Taitem Engineering. I specialize in plumbing, sprinkler design, a little bit of mechanical. That's kind of my next trade that I'm getting involved in. Um, but right now I'm going to be talking about a project or a couple of case studies where I did a central heat pump domestic hot water systems, as well as some general kind of rules of thumbs for designing the system and some lessons learned. Um, I had to figure out how to drive the PowerPoint. Um, okay, so something I look at when I'm designing a central heat pump domestic hot water system is the first thing is Legionella. I'm always looking at this. Legionella typically thrives at the target tempered water temperature. So for most projects, and especially projects with people with compromised immune systems or younger children or the elderly, I like to store water at above that temperature. I also like to mix that down because the same people that are at highest risk of Legionella are also at the highest risk of scalding. So I always store at 140 as my target temperature, and that'll kill off Legionella within 30 minutes. Another good thing about storing at 140 is it gives us some effective, a little bit more effective tempered water in our volume because we'll be mixing that down to our target delivery temperature. Another thing to consider with heat pump water heater systems is that they have a slower recovery rate when compared to a more traditional natural gas or fossil fuel boiler system. So when you're designing these systems, you gotta play the game with storage versus recovery rate, and you can kind of balance that. So this over here, you can see the at the bottom, you can see a sizing chart from ASHRAE's HVAC Applications Handbook. And I always try to play the game of balancing how much storage we have in the project versus how much heat pump generation we have. Um, you don't want too much storage. You can try to reduce the amount of heat pumps you have by increasing the amount of storage, but that only takes you so far. Storage is expensive. If you're getting above 120 gallons, then you're paying for ASME tanks, and those get very expensive very quickly. They take up a lot of space. And you have increased standby losses. Another thing to consider, we've been running into a couple of projects recently where you're storing water on floors, on the upper floors. And if you're holding 500 gallons of storage, that's close to 8,000 pounds when they're full of water. So that's another thing to consider, is you usually have increased structural components. And then the last thing is I try to limit the amount of electric resistance. If I can design a system that uses 0 supplemental electric resistance, that's great. But if we do need some supplemental electric resistance, I try to keep that separate from the backup electric resistance if that's necessary. Usually that's either done with a control scheme, or in some other projects in the case study I'm going to be presenting today, we'll separate those with just a complete manual switchover with breakers and valves. So another thing I look at when designing these systems is the refrigerant types. There's 3 main refrigerant types in the United States right now that central heat pump domestic hot water systems will utilize. The first one is R134A. Now, this can produce hot water up to 170. That's kind of our target, our what we use for the temperatures for these hot water, but they can probably go up hotter, maybe 185 degrees. But they have a pretty high global warming potential. And when your project is looking at embodied carbon, that's definitely something to consider. And another negative with R134A is that they're not great for cold climates. They can only operate at an ambient temperature of 40 degrees Fahrenheit. Anything below that and they won't work. So usually in the climates we're designing in, we only use these for split systems or cascade systems, where this would be the indoor unit, or if you're using a water to water system. The second refrigerant is R410A. So this can operate at a colder ambient temperature, -5 degrees Fahrenheit, or even a little bit lower with some of the more modern systems, but they can only produce hot water up to 140 degrees Fahrenheit. And that's really kind of the upper echelon of this refrigerant. A lot of them are 130. And when you start factoring in heat exchangers, it's even going to be less than that. So typically you would need supplemental electric resistance to boost that temperature up to our target. This also has the highest global warming potential out of the 3 refrigerants we're going to look at. And lastly, you got R744, which is CO2. So this can produce hot water at 170 or higher, and it can operate at really low ambient temperatures. Realistically, any ambient temperature in our climate, these will operate in. We have a couple of systems, and one of the ones we're going to talk about that operated throughout the entire winter in upstate New York. They can go down to minus 20 degree Fahrenheit, and we even have some quoted temperatures below that. Another thing to note is that this has a GWP of 1 because you're comparing CO2 to itself. One thing to note with these is that you can't, with modern pieces of, or with the current pieces of technology, you can't do a split system because they have a high operational pressure of, I think it's 1400 PSI, which is just way too high for modern split system line sets. So this is the case study we're going to jump into. It's Vicino Art House, or Vicino Ithaca Art House, because there are two. It's in Ithaca, New York. So the project is a 5-story, 124 unit building. It's podium style construction, and it's 100,000 square feet. So the top 4 stories are apartments, and then the first floor is parking garage and some commercial spaces, as well as a studio space. And this was designed to NYSERDA's multifamily new construction program, Tier 2. And the status is complete. This has been occupied since November. So when sizing this system, I sized it under the following assumptions: 1.5 GPM shower heads, 104 one-bathroom units with an average of 1.8 people per apartment, and then 22 bathroom units with 2.5 people per apartment. There's also 8 commercial washers, 2 on each of the residential floors. And this output a peak hourly usage of 1,248 GPH and a max daily usage of 4,740 gallons. And we use a couple different sizing calculators to come to this number, but they're all about the same. They're all based off of the ASHRAE sizing and HVAC applications. So we compared we looked at 4 different systems for this project. The first one was a central ground source heat pump system. We were driving a lot of piles for this project, so we figured we might as well look at using a geothermal system. The cost came out way too high for this project, and we ended up going away from it. The second one is a central R410A air source heat pump. And this is being designed in 2018, and the technologies just weren't really around. LG didn't have a hydro kit that could produce hot water, or our target hot water at that time. There were a couple other systems that were really just reverse chillers, and the manufacturer said, yes, we could produce hot water at 130 degrees, but that producing even at that temperature would cause premature burnout of the compressors. We decided that the technology just wasn't really there at the time, so we decided against it. The third system, and this is the system we ended up going with, it was a central CO2 air source heat pump system. So right here, it's a Sandin system, or Sanco now, but they were Sandin back when we were designing the system. And this is a split system with multiple, or with a large array of heat pumps. The last system we looked at was a semi-central hybrid water heater system. So this design would have included ducting, a chain of these together, venting the supply and exhaust air for the heat pump into the hallway, and adding a little bit of supplemental electric resistance. We decided that was just way too complicated. If we didn't get the space heating completely balanced, we could have some cold spots. And we figured that since we were ducting inside the building, cooling that space down, that the impact on our overall COP was just going to be too great, and we decided against it. So when sizing these systems, I like to size the peak storage, or we're working with Sanco, we size the peak storage or the total storage to deal with the peak usage. And that's an hourly usage of 1 to 3 hours, typically in the morning. So we needed a total storage of 1,248 gallons roughly. And then sizing the number of heat pumps, or the generation, we choose whichever of these quantities is the largest. The first one is the capacity to recover the max daily usage in a 16-hour period. This allows for the heat pumps to rest and defrost, and makes it so we're not pushing them to the max 24/7. Or we'll size the capacity to recover the peak usage in 4 hours under normal capacity, or 6 hours under derated capacity. And these Sanco systems at 15-degree ambient temperature start to derate from 4.5 kilowatts of effective generation to 3.5 kilowatts. So we ran into a couple of design challenges when initially designing this project. The first is that the water will exit the building envelope just because it can't be a split system. So we're actually sending the potable water outside the envelope, and that adds a big risk of freezing. The second one is that we wanted to add 100% backup to the system just in case there were something that would happen to these heat pumps. And lastly, we ran into space limitations. Like I said, there's a lot of storage required for these projects. And we didn't have much space for our domestic hot water plant, and that's pretty typical for these projects. So the first one, freeze protection. As I said, water exits the building envelope, and it presents a risk of freezing during really cold temperatures when the system's operable, but it presented a really large risk of freezing when the power went out, because you have this cold water sitting outside the envelope, just losing energy and getting close to freezing when the power goes out. So we to deal with the freezing risk during normal operation, we just added 2 inches of insulation and self-regulating heat trace tape. And we have some data monitoring equipment on site over the course of the winter, and we saw that heat trace tape only kicked on pretty rarely, only a couple minutes when it got really, really cold, below freezing. And it was only around 100 to 200 watts of power. Second, when the power goes out, the way we deal with freezing is we have an automatic drain back system. So this incorporates some normally closed and normally open zone valves that will revert to their natural state when the power is lost, and then some automatic air vents and vacuum breakers that allow for water to be purged from the system and air to be purged from the system when the water naturally refills at street pressure. The second design challenge we ran into is space limitation. So this right here, this is the domestic hot water room. As you can see, there's not a lot of space. We have 2 500-gallon tanks and 2 120-gallon tanks take up most space in there. So the way we tried to address the space limitation is that we actually combined 2 different systems. So the backup electric resistance is housed within the 220-gallon storage tanks that we need to increase the effective storage of our system.
Clark Nixon, the project manager for the USDA.
The lastly is 100% backup. Like I said, this is new technologies, and we wanted to add something just in case we needed to service the heat pumps prematurely or if something happened. So we do have 100% electric resistance backup. This is sized to just be a 1-for-1 replacement. So it's designed to, it's 2 36 kilowatt electric resistance elements in the 120-gallon water heaters. So these water heaters are piped in series. If we need to switch over to electric resistance, you would deactivate the central heat pumps. You would isolate them, drain the system of all the water, and then open up some ball valves and turn on power to the water heater and a circulator pump. And then we would have a 1-for-1 replacement until the heat pumps came back on. And we wanted to make that a fully manual switch over, so it was intentional. We didn't want anybody to flip this on because they thought it should be on. There's a process that needs to happen to completely switch this over. So this is the final system selection. We have 2 parallel systems, 8 heat pumps on each side, total of 16 heat pumps, 1 electric resistance water heater on each side, and 1 500-gallon storage tank with a target temperature of 150 degrees Fahrenheit. That 150 was used to kind of increase the effective capacity of the system a little bit more. And then secondarily, we have the 2 36 kilowatt electric resistance water heaters that are housed within those 120-gallon tanks. So this is a picture of the isometric on the right from our drawings, and then how it's installed in the project. You can see there's a lot of piping, not a lot of space. And then this is the heat pump array, all 16 heat pumps out here. So system install and troubleshoot, system install and operating troubleshooting. So that was the design challenges we ran into when designing the system, but we also ran into a couple of issues during install and operation. The first was this automatic drain back system. So the automatic drain back system worked great in getting the water out of the heat pumps. Power cuts off, the system will completely purge of water in like 1 to 2 minutes. Way more than enough time to get the water out of the lines before they could get a chance to freeze. The issue was that when they would refill, some air would still get stuck in the lines, even though we did have the automatic air vent. It could cause an airlock at some of the pumps, and they just would go off on high pressure. The way we address that is that we have kind of a way to alert the staff that there was a drain back operation, which is just one of those leak detection systems that'll send a text message to your phone, and then we'll just have the staff go and walk around and verify that the systems are operating properly when we do have a drain back. One thing we did verify over the course of the winter is that if this drain back operation, if we had a heat pump that would go out on an error code during a drain back operation, they would not freeze when sitting in the error code because we would have enough thermal energy drifting through the lines. The second one is condensate, drip, and freezing. So these pieces of equipment produce a lot of water from the drain pan, especially when it gets below freezing. For the system as installed at Art House, we've been working on a couple of solutions to try to keep that from dripping on the units below and on the piping. But for future projects, we're either just mounting them all on quick sling ground mounted racks or staggering the heat pumps. Another thing we ran into was during construction, we found that when the load was really low and we had the recirculation system turned on for normal operation in the building, it would churn the water up in the storage tanks and they wouldn't be stratified. And we wouldn't be getting any fresh cold water into the system. So when the heat pumps would call, the tanks would drift below the target set point, but they were completely churned. So it would be pulling tempered water into the cold water inlet. Since these heat pumps are single pass, they wouldn't be getting enough heat transfer across their heat exchanger and would go off on high pressure. So the way the contractor dealt with this was they just turned off the heat pump, switched to the backup electric resistance during construction. And as soon as the building became occupied, they switched it back to the heat pumps and we didn't have the issue. Another thing we ran into was pipe length layout. So originally we were planning on penetrating the wall with a manifold that was inside and individual home runs outside the building envelope. This would have been 32 different pipe penetrations, and we found that just wasn't practical during construction. So we ended up converting it to 4 pipe penetrations, 2 supply, 2 return, and then headers running out to each heat pump. But since we're piping this in reverse return to get effective balancing without check valves or without balancing valves, we got close to the maximum pipe length of the system. This was dealt with just by working with the manufacturer, upsizing some piping. Since the heat pumps have their own integral pump, we really need to be cognizant of the total pump head. And we just increased the pipe sizing, worked with the manufacturer, and we're able to get this to work. But that is something that you need to you need to consider when designing these systems. Okay, so we also have some measurement and verification happening at the system. We don't quite have enough useful data right now to draw any conclusions, but we are measuring at a lot of different points, and hopefully we'll be able to draw conclusions about like total system COP and balance the system a little bit more properly. So we're taking data measurement at the heat trace tape, recirculation pump, and all 16 heat pumps individually, and that's for the power measurement. We're also taking temperature measurements at the cold water inlet to the system, cold water to each heat pump array, hot water to each heat pump array, hot water out of each tank, hot water to the mixing valve, and tempered water to the building. So all of that data would be really useful for me as the design engineer, but it'll also, some of that data will be useful to get the effective COP of the system. And lastly, we have flow rate, cold water to the domestic hot water plant, and cold water to one of the heat pump arrays. This is just a screenshot from our EGauge data. It just shows that it was -5°F out for a couple of these times, and it shows that we're producing our target temperature even when it's -5 out. This is just 63 degrees Celsius This is water being sent from the heat pumps back to the storage tanks. And this is just the total power. So you can see that some of the heat pumps arrays are staging on. You can see when it goes to 50%, that's one half of the system turning on because one tank got a little bit colder than the other one. These should be in harmony, but this just kind of shows that the system isn't fully balanced yet. Okay, so I'm going to go into a couple other case studies. This is going to be a lot briefer than the Art House project. These are both in varying stages of construction. So this is a Cottington Road Community Center. This is the project is going to be, it's an addition on an existing building. It's going to be about 10,000 square feet of addition and 13,000 square feet total. And this is a community center, but it's also classrooms. And the status is still in pre-construction. So this is the system, right? So it's 3 hybrid water heaters, and we're ganging these together and ducting the supply and exhaust of these hybrid water heaters to a gym space next door to where the domestic hot water plant is. So there's also a large commercial kitchen, and the way we're addressing this is that we are adding a booster heater. So we're sending a tempered water loop at a lower temperature than normal because scalding is a risk here. And then we're going to boost to 140°F at the commercial kitchen. And that's just with electric resistance tankless water heater. And that is sized to completely deliver hot water at 140 degrees to all the critical loads to keep the kitchen in health code compliance at all times, even if we deplete all the hot water in the project. And then lastly, it's Asteri Ithaca. So this is done by the same developer as the Vicino Art House. It's Vicino Asteri. This is also about a mile away from our office. It's going to be a 12-story, 200,000 square foot multifamily apartment, 180 affordable housing units. And then there's also going to be a conference center, retail space, and a parking garage on the first 3 floors. So the residential floors are complying with NYSERDA multifamily new construction housing tier 3, and then Energy Star's multifamily high-rise program. And the project complies with Ithaca's new energy code supplement. This project's under construction, but it's really early in construction. They've demoed an existing parking garage, and they're starting to get some of the under slab structural components in there. So we're a ways out from getting to the DHW system. And this final system selection, this is a very large project. And this actually will probably go underneath some revision because we're planning on converting a large commercial kitchen to all electric. It was gas at one point. And that will probably be added on to this system. But the way this system is designed, it's 2 410A heat pump systems. They're both 540,000 BTU per hour. And we're using glycol as a working fluid for this system, separated by a double wall heat exchanger. And then we also have an electric resistance boiler using a close space T injection type arrangement as supplemental to bring that up to the target temperature of 140°F. Because right now we're probably going to get at 125 just with the heat pumps. The secondary system is and this is just when these go down because of ambient temperatures, would be 2 electric resistance boilers. So we're hoping that this really doesn't kick on very often, but if it gets below that -5°F, then we will need to kind of rely only on electric resistance. And these boilers are a 90 kilowatt and then a 108 kilowatt. So a lot of energy going to those. And this is where James would jump on. I don't know if James is on here.
He is here.
He is, okay.
So we can
Excellent.
give it right to Jim.
Yeah, James, let me know when you want me to switch slides.
Yeah, do you want me to just take control of the screen and I can share because I have mine up? Or
Yeah.
What works for you?
That works great.
Perfect. How does that work?
I'm just trying to figure that out as well. Okay, here we go.
Is everyone seeing mine?
Yes.
It's hard to know if you're looking at the same screen.
Yeah, that's true. Yeah. We are seeing yours because I just switched mine.
Okay. Thanks, Brandon. I caught most of that, which is good. So I won't repeat anything. So that was a lot of, I guess, the in the weeds, and where I'm going to take over is what's available now, and particularly at early stage planning, what we're seeing go in on some multifamily projects now. The state of New York has taken a lot of their incentives and moved them to all electric everywhere. So one of the difficult pieces is the hot water system on some of these buildings. And these are kind of the three types of systems that I'll kind of talk through. The central CO2-based system, Sandin being the one. On Ithaca, there are some other manufacturers. The middle one, we're seeing more and more now with the LG VRF system, and then, just using off-the-shelf integrated hot water heaters, how those can work. So generally, some of the CO2-based systems, you have the Sandin system. That's more of a residential size, and you need a lot of them. As you saw on the Ithaca building, you just need a lot of outdoor condensers in order to handle the load. So you have a lot more hot water lines to run out the building. You have a lot more just piping to install. So the cost of the Sandin is in particular on a big building, just the amount of the units you need. Mitsubishi has one QAHV that's come out, making sure there's a freeze protection availability. But we are hearing teams are starting to use that. I just don't have exact firsthand knowledge. We have not had teams and engineers get through the frost protection issue, so it's not a unit we've seen. On the CO2 side, we are seeing the one on the right on a couple projects. I suspect, based on the size, the capacity is bigger. I also think it's more expensive. It's kind of trending more toward the commercial size system, both in size but also in cost. So kind of making sure that it fits within the budget of the building is something to keep an eye on there. So those are CO2 systems. Because they're CO2, high pressure, you have to run the hot water out to those units. Second one is the LG VRF system. What Brendan was talking about on the Ithaca design is back 3 years ago, they only had what they called the K2 hydro kit. They now have one called the K3 hydro kit, and that's the one I'll talk about, and basically how that works. But essentially, you have an outdoor VRF system, which contractors are a little bit more used to. They've been on the market a while. You get larger capacities, and you just need less equipment outside, albeit it's a bigger piece of equipment, but it can go on the roof or it can go in a single spot around the building. You're then just running refrigerant lines between the outdoor unit and the interior space. We've gotten some simulations from the manufacturer on COPs, and they're estimating just over 3 on a COP for a system on a 100, 150 unit building in Rochester climate zone. So how does it work? You have the outdoor unit. It comes into these K3 hydro kits, and then it additionally boosts the temperature. The pros is you don't need to run hot water out of the building. You have less outdoor units. The cons being you're now putting refrigerants back in. You have the higher global warming potential refrigerants, and then the controls and operations to keep in mind on those as well. So the reason, going back to Brendan's slide on the refrigerants, they're able to both get the low temperature and get the high or the low ambient operating conditions and the high temperature, is they actually mix both refrigerants. The R410A refrigerant runs between the outdoor unit and the hydro kit inside, and then the hydro kit inside has an additional R134A cycle that takes additional heat from that R410A and puts it into another loop. That water loop then goes to another heat exchanger that then brings the heat into the storage tank. So still a decent amount of, kind of going back to this slide here, still a decent amount of heat exchange happening. You have 2 different refrigerants and then heat exchanger. Still need larger storage tanks because the heat pumps do work a little more slowly. So that would be the same. So what we were able to do is get some cost comparisons on the installation of 3 scenarios. We used the Ithaca Art House and the pricing from the actual installed stand-in system, which is the top row. And then we also had pricing come in on the LG Hydro Kit, and then also compared it to a base gas boiler situation, and kind of broke it down between equipment costs plus the piping and install costs. So the real, I guess I'll call it, savings from the LG Hydro Kit versus the stand-in in particular is lower on the piping and install because there's less outdoor units, less piping. Equipment cost, I'll call it roughly the same order of magnitude wise, and equipment costs about double from a gas boiler situation. Looking at the kind of cost premiums on the far right, kind of that $100,000 or the $80,000 to $100,000 range, that might seem a lot, but in particular in New York, where this is a integral system to say bump up some incentive levels, you're actually getting more incentives back than you're paying for on a system like this. So for instance, the new construction housing program in New York offers $4,000 a unit for housing projects to do their highest tier. An efficient heat pump system like the LG or the stand-in is one of the key components to get to that tier. So you can get an extra $2,000 a unit by using a system like that. So you can kind of pay for this upgrade, but also a couple other efficiency upgrades, and you can kind of hit some of those higher tier programs.
James, you just go back real quick. One thing I wanted to also point out here. So Art House is completely fossil fuel free. So one thing that's not included in this gas boiler baseline is the full natural gas service to the building. And that's something that's going to be typical in a lot of projects at this point, especially in Ithaca, because all new construction projects need to be fossil fuel free.
Yeah, I think that's key as well. And as the gas infrastructure starts to be used less and less, like who's going to actually pay for those systems? Is the gas utilities really going to want to? Like, there's going to be a disinvestment in fossil fuel infrastructure over the next 20 years because it's going to be swapped to all electric systems. So certainly on new builds, I wouldn't even look at that baseline. Maybe we shouldn't have called it base gas boiler. We should have called it old school gas boiler. It's really the electric systems, how to get those to work in, because you're really investing in a stranded asset if you bring gas to the building, if you do the gas system. The flip side is it's still operating cost wise might be about neutral to operate these systems because gas is still fairly inexpensive, and the electric systems, while efficient, might be about a cost neutral to operate. So if you do have a gas system, one key would be to make sure you're designing it to be swappable in the future, so that 10 years from now, when maybe there's better technologies or swap systems that are more swappable, that would be something else to make sure to design in. So those are kind of the central plant options. Other scenarios would be using individual heat pump hot water heaters. A couple ways to share the cost would be put them off the corridor so that you're not stealing heat from apartments, and then to potentially share them across multiple units. So this is a design we've seen on a couple projects where you're still owner paid on the hot water, but you're using one tank off the corridor to kind of share amongst the multiple units. I think we've seen an 80-gallon tank used for 4 apartments. So that's a possibility as well. When designing around shared heat pump water heaters, definitely making sure there's enough air transfer because you're stealing heat from inside the building. That's why the corridor becomes a decent sink for that, because it gives the corridor free cooling all summer. And then in the winter, you would need to make sure you're sizing the heat pumps for the corridors to make up for that. I think, Brendan, you've mentioned putting them in laundry rooms or maybe
server rooms and cooking, like I'm thinking cooking, but like large commercial kitchens might be a place as well where you might have some waste heat, to kind of locate them in those areas.
So the last comparison we did was looking at, well, what about just going electric resistance tanks? That seems easy and cheap, right? And on the first cost, it is, but we ran a couple comparisons and just wanted to show the operating cost difference for a couple different apartment types, the top table being a 1-bedroom, bottom being a 2-bedroom, between, well, what if you had an electric resistance tank and what if you had a heat pump water heater? Looking at the domestic hot water line, you can see the electric resistance at 200, on the 1-bedroom, $268 a year, drops considerably to $100 a year in the heat pump water heater scenario. The two things to note are the heating goes up. So it goes from $134 to $188 a year because you're basically paying to heat the air that hot water heater is stealing the heat from to put in the water. But you also get a reduction in cooling because you get a little bit of free cooling. I've heard it likened to basically you have a small air conditioner running all year round. So you got to be able to make sure that you can deal with the sound and deal with the temperature drop coming with a system like that. So a couple case studies that I will give nothing but one photo and some description of would be like, well, who's putting these systems in? So here's some projects in various stages. We have this project in Cicero is using the Sandin system, and I believe it's a 50-unit apartment building, senior housing, all 1-bedrooms. I think it has 8 outdoor Sandin systems and internal storage tanks. That one is in construction. Recently entering construction, Pilgrim Village in Buffalo. This is kind of a 2-building project. One's a 100-unit senior, one's a 130-unit family building. The design on these was both central Sandin systems. We just got the submittal yesterday, and the submittal was for the LG VRF system. So the subs and the contractors kind of are pitching to swap that out, and engineering team and ourselves are okay with it. So that seems to be a swap. And I think on the family building, they had upwards of 20 or more Sandin systems that I suspect are going to come down to one LG system as far as an outdoor unit. They had also built a shelter to cover the Sandin system that wouldn't need to be included on the VRF system. So that's a cost savings to the project. Another project in Buffalo in late design, just submitted for permit, is Pan American, a 150-unit project in Buffalo, and that is using, I believe, the LG VRF system as well. There's kind of 3 different segments of the building, and I think they'll each have their own hot water system. And then the last one to round it out, Baird Road is a Buildings of Excellence Award winner. It's 76 apartment units, and that is using the distributed heat pump hot water heater solution. So it has one 80-gallon tank for 4 units that they then have hot water rooms spread out throughout the corridors. So just wanted to show that these scenarios are happening throughout the state in kind of various size buildings. That's all I had. I guess, do we want to open up for questions?
Yeah, I think let's open it up for questions. Thank you, Jim, and thank you, Brandon, for your great presentations. I'll leave it up to participants if you want to unmute yourself and ask a question. As long as we don't have many people talking all at once, we can try it that way. Otherwise, you can type in your questions in the chat, and I'm happy to read them out loud. And while we're waiting, I have a couple of questions or thoughts as well. So the one thing to think about here with passive house and domestic hot water that I think is really important and can't be overemphasized, in my opinion, is that the energy load profile of a building drastically changes when we go passive house. So traditionally, the loads of a building were mainly driven by heating and cooling. But now with passive house envelope measures, those have been shrunk down so drastically that the domestic hot water really takes up, the domestic hot water and lighting and appliances end up dominating the load. And so if we're designing for low source energy, because we want to reduce the energy overall, and we've already kind of tapped out on the envelope, the domestic hot water becomes really important. And then the other thing is, because we do have passive house projects that are still wanting to use electric resistance hot water, because as Jim said, it's for affordable first cost, is that specifically in multifamily buildings, kind of medium size, where the occupancy density is fairly high, those buildings are already largely internally gain driven. So, you know, it's cooling targets that we have to look out for. So if we're adding, you know, 46 electric resistance water heater tanks in the building, we just increase our internal gains that much more. So things to think about and reasons to look at the systems that Brandon and James were talking about. But then also my question was back to the Legionella piece, because I've seen programs promote like I want to say like 120 degree set point or 125 degree set point, Brandon, in I guess more single family home applications. But can you speak to that a little bit? Is that like a dangerous thing to do?
Well, it's as dangerous as you want to consider Legionella. It's anywhere, any situation where we're dealing with kind of people that are at higher risk. I always try to store above at least the temperature that Legionella thrives at. So Legionella grows best at like 120 degree Fahrenheit. So you're actually like providing the best case scenario to grow Legionella, which is the worst case scenario for who you're designing for. But yeah, in like residential applications, most people just set their water heater at that. If you set it at 120 or below that, you don't need a mixing valve necessarily. Most people don't put in a mixing valve. So that's one kind of benefit there. But I design all my systems at around 140. I mean, you have increased standby losses, but you also get to, with these large central systems, you get to reduce the amount of overall storage. If you can go from a 700 gallon tank to a 500 gallon tank, that's awesome. So, yeah.
Yeah, that's good to know. Thanks. Any other questions or thoughts?
I have a question regarding just home performance upgrades in existing single-family houses. Are there people on this forum that have had personal experience with putting an air source heat pump water heater in their basement? Has it added quite a lot of, extra white noise? Have people found it objectionable, or is it cool?
We've heard from like anecdotal evidence in our firm that if the heat pumps, if they're operating how they're supposed to be, the hybrid heat pumps aren't that noisy. I believe they're around 60 decibels, which is like an older fridge. So if it's in your basement or somewhere remote, or in your laundry room, that's another great place in your house to put it, is in the laundry, somewhere that has like internal heat gains. Then it's not going to be that out of the ordinary. But we've also heard that some of these pieces of equipment operate really loud just because of like bearing failures, or they get loud. And then it is noticeable. My manager has one at his house, and it's been driving him nuts, and he had to warranty it out. So, and I think that might just be, it's something that popped up recently, and it might just be a batch of manufacturing, like a manufacturing batch that caused that issue. I don't know if it's all heat pumps, and that's just kind of anecdotal evidence.
Is the Sanco 2 still the only water heating system that's split, where you can get the heat pump away from outside the house?
No.
The Sanco 2 is pretty darn expensive.
Yeah, it'd be there, I think $3,000 for the heat pump. You can use your existing tank if you want. No, there's other systems out there, but Sanco is one of the more reliable residential systems. There's larger, like James presented, there's LG, Mitsubishi, there's some really large reverse chillers. And then there's I think like Solaris makes one. There's a couple other ones. They're kind of niche pieces of equipment, but there are other pieces of equipment out there.
Brendan, is the Sanco the only CO2 refrigerant unit though on the market?
For that size application, yeah. But there are, Mitsubishi makes one, not fully convinced yet on its operation in cold climates, because I don't know if they have a way to address power outage and freeze protection other than putting it on a generator. And yeah, James pulling up his presentation. So the Watts one is also a CO2. So these are the three that I'm aware of that are CO2 based, all single packaged, and you would send the potable water outside the envelope. Just, I believe that's just due to the high operational pressure of the CO2 refrigerant.
And I did get a question coming in through the chat from Robert. Can DHW by heat pump also help with dehumidification? If so, can we design the system to take advantage of that?
I don't necessarily know if they provide any like practical dehumidification. So unfortunately, I can't provide any better answer than that. I mean, I think if you were doing dehumidification, you would want to, you'd be looking at like one of the hybrids. I think that's one of the only applicable ones. So maybe if you got on the phone with one of the manufacturers, they might be able to kind of give you some information as to whether it will provide some dehumidification or not.
Yeah, I can say anecdotally, my basement is drier than it used to be, but by how much, I don't know. And also regarding the noise question, I am glad it's in the basement and not in like a closet off of, a central kind of location. And it definitely cools things down in our basement as well. So
How much?
They're 4,200 BTU per hour.
How much does it cool things down? I don't know,
Yeah.
because I don't really spend a lot of time down there. It's just kind of an unfinished basement for storage, and it has a boiler that of course kicks off waste heat. So my house happens to not be a passive house, it's an older home, and we have a boiler, and although we do use heat pumps as well, I should say, we still use the boiler somewhat. And so we, can take advantage of whatever waste heat it kicks off down in that unoccupied space by having our integrated heat pump water heater down there as well.
Thank you.
Brendan, I have a question. The building that you showed with the Sandin units, the bank of condensers outside, was there any issue with the, in terms of harmonics, noise, or any weird sound issues occur with that setup?
No weird sound issues. So that's on a wall, and if you were to kind of look towards me when I was taking the picture, that would be the parking garage, and that's all kind of exposed towards an inlet. So there's no harmonics. That actually mounts all the way there. The heat pumps are pretty close to a window right below the heat pumps, or there's a window above them. No issues with the harmonics. It's cold in front of there. If you were to stand in front of there, especially in the winter, like below zero, and you stand in front of those heat pumps, you feel it for sure. But there's no issue with noise. You can't even really tell that the heat pumps are on when you're standing there. They're really quiet. I think 49 decibels. And we have good vibration. We call it for good vibration in our spec to isolate from the quick slings, and there's no harmonic issues there. But if you like, when I go and because it's a mile down from our office, I'll check on them every once in a while because it's a cool project. I want to make sure it's running properly, and I have to go look at the control panel or the little LED or LCD screen to see if the heat pumps are operating, because you can't tell by just looking at them or listening to them.
I have another, oh, go ahead.
Well, thank you. In regards to the electrical demand, it sounded like, or you mentioned that you created a redundant system of just electric resistance heating. Did you get any pushback from the electrical engineers on the project saying that, that's excessive load to be designed to? Or was there any problems with the electrical portion of the design?
It's definitely an additional load for the project. So I try to, when we think that we're going to need supplemental electric resistance or use electric resistance, I bring that to the table with the electrical engineer pretty soon in the project. I think with this one, there was a little bit of sticker shock, I guess, with the electrical load, but we were able to make it work. The one that it was a major concern with was the Vicino Esteri project, and that's because we had close to 200 kilowatts of electric resistance, all going up to all in this penthouse. I mean, it's quite a lot of power. But that's also a 12-story building with a like a huge electrical service, so it wasn't as big of a deal. It's definitely something to bring up, though. You don't want to like go down the hall to your electrical engineer 5 minutes before CD drawings go out and say that I'm going to add 100 kilowatts of electric resistance. They're going to throw you out. So
It happens all the time to me. Somehow mechanical engineers, they always forget, or plumbing. But thank you.
that's also something to work with your plumbing engineers if they're designing this system, because their plumbing engineers aren't necessarily used to designing with large amounts of electric resistance. I mean, you can have tanks in each apartment, or it's traditionally natural gas boilers. So this is something for everybody to learn and kind of grow with the process when you're designing these systems.
Thank you.
My question's about recovery. So in the scenario where 4 apartments are sharing one unit, one 80-gallon tank, and if it's like a time where everyone's showering, doing dishes, doing laundry, or maybe they don't have in-unit laundry, either way, it takes these units longer to recover than typical like systems that we're used to. So do they just get set into a hybrid mode that recovers them using electric resistance, or are people just having to get used to slower recovery times?
I usually, unless I'm designing, James can speak to this too, but unless I'm designing a system I know exactly what the load is and it's only one person's doing, like an office, for example, where it's not so critical, there's no showers. I set it to hybrid mode almost all the time, because you get that. I mean, the algorithm within these units is pretty smart. So it'll kick on when it needs an extra boost. And when these units are in hybrid mode, they have a higher recovery rate than a traditional electric resistance water heater, because they have the 4,200 BTU heat pump and the 4.5 kilowatt electric resistance element. And they will operate in harmony if necessary. So if it's a shared between apartments, I definitely set it to hybrid, or call for it to be set in hybrid mode.
I think mine's in hybrid, but I always feel like we're running out of hot water. That might just be us using a lot with small kids.
Yeah, and I can give the non-plumbing engineer answer, because I'm not a plumbing engineer, so I can't give that answer. 2 things to keep in mind when designing the all-electric systems is, if a system's used to being a central boiler, the differential cost between loads might not be all that different. So you might just use a rule of thumb and say, oh, I got a really big boiler. But if you take that same approach with a heat pump system, you may really over-design it. So being really conscious about the distribution system and the actual loads of buildings. It's a separate presentation, but I know we've seen a NYSERDA panel talk about real hot water loads on buildings, and that they're a lot lower than what they may have been designed for. So staying conscious of that, because you can really save some costs by not over-designing. And then also just not having super high flow rate fixtures is another way to kind of make sure you get that recovery.
Yeah, to speak to that, I usually size the heat pump system to deal with what our kind of estimated peak usages or estimated flow rates are at like normal capacity. And we'll throw in some supplemental electric resistance to kind of pick up that slack during really high demands, because these systems, if they're oversized and sized to deal with the absolute highest demand possible, they'll operate inefficiently 90% of the time, because they're kind of they're too large of a capacity. These heat pumps really like to be sized pretty close to what the average operation would be, and not way oversized. They just won't operate right.
And on the single family like retrofit scenarios, most of the heat pumps are 240 volts, I believe. Some of them are starting to come out that are standard 120, and that they may not have as much of electric resistance, but the real benefit is you might not need an electrical upgrade on a house to put them in. And that, I think, starts to really change the game to start getting more of an adoption on the single family market, so you don't have to run into those various things.
Has anyone run into supply issues with the Sanco 2? I just read recently on some website I was looking at that there's a long delay in supply for the Sanco 2s.
I haven't run into any projects that have supply issues. We have a project going on down the street that's using 18 of them, and I don't think they had any issue getting a hold of the units.
Okay.
But I did go on a walkthrough with a contractor, and they had an issue getting a hold of a supplier, so that might be a supply chain issue in disguise.
Thanks.
Another question came in through the chat about domestic hot water circulation. With a heat pump, what is the preferred DHW circulation plan? Bathroom sink as well is the follow-up. And not sure if this pertains to like a single family scenario or a multifamily scenario. So whoever asked the question, Robert, feel free to unmute yourself and elaborate.
Well, there's a lot of losses for a continuous circulation, domestic hot water, and I'm curious what the plan is, since that heat pumps are very sensitive. As far as they're not as strong, they don't have the high recovery as a gas system.
Yeah, I mean, the first step is doing like a smart box recirculation system. Really, there's a couple other presentations that have been given on just like how to like really minimize the amount of recirculation lines you have and losses in the system, and designing a smart recirc system. But then you also, I always like to use like nice electronic mixing valves that have a really low delta between your cold water temperature and your target temperature, so you can really put most of that hot water or tempered recirculation water back into the system and not sending it to our domestic hot water plant to be reconditioned. And lastly, you just really need to, some systems call for, especially like Sanco systems or other heat pump systems, they call for dealing with the recirculation with just a separate water heater, electric resistance, or a hybrid. The way we handled it at Art House is that we, let me see if I don't have the presentation up anymore. The way we dealt with it at Art House is we kind of dumped it into the 120-gallon storage tank that is in series and feeds the cold water for the 500-gallon storage tank. And we also have a heat timer mixing valve with a low delta T between your delivery temperature and your return temperature at your cold water. And what happens is we do end up dumping a bit of recirculation water back into our hot water tank, but that tank is fully charged with no stratification at 140 degrees. And we found that the volume is so low that it really just kind of mixes the tank down, maybe 130, still above our delivery temperature. And then the system itself will pick it up without getting that recirculation water at its cold water inlet, which could be a parasitic load for the heat pump.
So the circulator pump is on a timer, a motion sensor, or
it's an Aquastat. We have the pump set in an Aquastat there to set it at 104, and we kind of just designed per code, but Aquastat style. Yeah. The tricky thing is that you want the recirculation to be running as infrequently as possible, but also these mixing valves, or all mixing valves, require constant recirculation. So it's a little tricky there to size everything properly, and you have to play some games and see which code you're trying to comply with the best.
Thank you.
I'm crashing your meeting because I'm here in Chicago, but I super appreciate all of the great content and things. I put it in the chat, but I just thought I would jump in and ask the question. We're kind of just starting. I work for an organization. We support a lot of utility programs like NYSERDA's. And we're seeing a lot of projects come in as all electric or passive house. And as these people are getting into it, there's a lot of heartburn around like actually cutting the cord on the gas supply. So it's less on a technical and more on like kind of a conversation team question is, what pushback did you get from different partners? And did you have any doubts yourself? And how did you overcome those kind of issues?
Maybe I'll take that one.
Yeah.
In terms of in New York, and this is where the psychology meets the technical. Early implementation is mostly psychology, and then the technical needs to support it. So NYSERDA, for instance, has had incentives for passive house and all electric for years, and almost very low adoption. So we work on nearly 80% of the affordable housing projects in all of upstate New York. So we're seeing kind of what's happening in various parts of the state. And in the low-income housing tax credit world, there's a disadvantage to be the early adopter, because if your costs go up and no one else is due, you're not competitive. But when when 5 people move, everybody moves. So if one person takes a competitive advantage, then everyone has to match it to stay competitive. And that happened last summer in New York around the electrification for a couple reasons. Policy being the big one. The state said we have to hit these carbon reduction goals and pass the Climate Leadership and Community Protection Act that had really aggressive targets to decarbonization. State agencies needed to start to meet those and built them in. Affordable housing being one where they're now saying in their design handbook, you shall consider being all electric at all times everywhere. They haven't quite mandated it yet, but by saying you shall consider, they're basically saying you need a really good reason not to be in order to get funded. So last round, we put in 35 or 40 different applications with teams, and about 70% of them went all electric. The round before, maybe 10 to 15% were all electric. Some of them got funded, being all electric, but now they're really just all going in. I had a 15-minute conversation yesterday with the top developers on one project going in a couple weeks, and it was basically, yeah, you should go all electric, and there's these central hot water systems that work, and they were like, okay. So like that sale was super easy. 2 years ago, I probably would have lost it. So there's a psychology around like, is it an option? Is it available? Many times the engineers are the last people to buy in on some project teams. But having people like Taitem and showing that they're in and installed and operational is really key on the technical side. So we need to show that they're working. We need to show that the options are available. The cost has also been helpful. That's why we wanted to do this costing exercise, so you can really see what the costs are. That they're not they are costs, but they're not insurmountable in any way. It's an investment in a different type of technology. So we've seen, there's always sticky wheels, but we try to play the unapologetic, greenie in the room to say, if we're not advocating for it, no one else is. So, I tell my team a lot, like, don't be afraid to be the one who brings up the new technology that some people on the call might be uncomfortable with, and push them. Like, keep pushing these project teams. And I assume everyone who's on this call is in that pushing world, because that's why you're on a passive house chapter meeting, right? So we all drank the Kool-Aid, we all believe, and if we're not pushing it, who is? So we are seeing more success aligning with incentives, aligning with case studies to say this is real, calling in the expertise of people who've done it before. Like, those are all things that help, to get through. But I think the policy side is starting to almost be the wave that drives the movement, because the policies that some of these states are committing to are very aggressive on carbon reduction. They have to do some of this stuff really fast.
Well, Jim, can I just, if we think about also some of our projects that are in Massachusetts that are like buying into passive house and committing to passive house, but then still going with gas for domestic hot water, that really points to it's the funding agency that's driving the decision. So as long as the funding agency is okay with gas, they're going to do it. And then even if they're signing up for passive house, not all of them, but some, right? So it's kind of an interesting case study working in both programs to see how the decision driver manifests the outcome.
Yeah, I think New York is certainly innovative on the all-electric piece because, like you said, other states might have passive house but allow a central gas system. And Phius, because they're countrywide, is being a little more open to not saying you have to be, and they might move a little later on the program standpoint.
And Daniel, I'm just curious, what company are you with?
I work for an organization called Slipstream. We're a nonprofit that does a lot of, I'm getting better at trying to deliver the elevator speech, but we do building science research, support energy programs, including a lot of the NYSERDA's energy finance elements. And I work here for supporting the local electric utilities affordable housing program. So just super helpful. And I think having, your experience to point to and kick the tires and say, no, real people in your same shoes dealt with this in very similar market conditions. And, it sounds like James was saying a little bit of like hard sell, like, all right, well, the train's moving, you can get on it or get under it. But the messaging element, and I think I wrote down the early implementation is 90% psychology. I think it's such a great takeaway for me from this.
All right. Well, with that,
I think go
ahead.
I think one of the minor points, it's probably not prevalent throughout New York State, but certainly, with things being delayed, a minor point is the final connection, utility connection for gas. We've had projects, in the lower part of the state that have waited weeks, if not months, for that final connection, which holds up, the developer from turning the project over, to ownership or occupying it. So certainly without that headache, that's a pretty compelling reason to not do gas.
Yeah.
Yeah, for market rate, that doesn't have affordable rules, like the stranded asset argument, I think is pretty high as well. May not get them all, but certainly that's why affordable is moving so fast, is because if they install new gas now, they're going to have to pay to rip it out in 10 years. They're putting these housing up for 30 years. They know they're going to have to pay to do these changeovers. But that's a big one as well.
Well, this is great. Thank you, everyone, for this discussion. And thank you, Brandon and Jim, for your presentations. Really informative. I'm glad we actually had the extra time to ask you guys questions. Unfortunately, the sponsor presentation won't be happening today, but we hope to get you that information on AeroBarrier at one of our upcoming meetings. And so I think with that, I posted the CEU code in the chat. I can tell you what it is as well. So it's 22201. And again, you go to www.phius.org/CPHC/self-report. That's also in the chat to self-report your CEUs. And yeah, I'm happy to leave this line open for a little bit longer, since we do have this meeting carved out until 6 p.m. if people want to continue any kind of discussion. But I'm also happy to give you back 30 minutes of your Thursday evening, if that works. And actually, before we wrap up, James Hartford, I don't know if we mentioned the seminary cidery tour earlier, but I think you have more details about it. So why don't you tell everybody about that?
Great, thanks. Hello all. So our slidery project, which received a Phius Design Award at the conference in Tarrytown this past October, and has won a couple other awards, including the Metropolis Planet Positive Award. We're going to have it as a tour in conjunction with the AIA Hudson Valley chapter that I'm now a board member of. And so we're going to have a 3-hour presentation, which will be hopefully good for 3 AIA continuing ed credits. We may, I'm not sure if, I doubt we'll have 3 for Phius CEUs, but certainly we'll have 1 at least. But the goal is to have basically an open house and lunch and tours at Seminary Hill Cider on May 14th, starting at 10 o'clock in the morning with breakfast, and then getting into the workshops. And it's a little bit pricey, or it's probably going to be about $100 per person, but it'll be a really nice event and a great way to come and see this project and learn everything about it, including the organic orchards. So we'll post information about the tour and talk. How's that?
That's great. Thank you. I'm sorry. I'm catching up on on the chat as you were talking. Yeah, that's very exciting. That's the day after my birthday, so maybe I can just come and like continue the birthday celebration.
I'll buy you a drink.
All right. Yeah, anyone else have any announcements that you want to share with the group? Anything exciting? Any projects you're working on that you want to talk about? Questions you have, topics you want us to address on future meetings. And I do see that Tony has some Phius announcements, so please go ahead, Tony. Take it away.
All right. So for those of you that have been doing multifamily, you know that Phius 2021 is requiring compliance with Energy Star multifamily new construction as a prerequisite, just the way they did for the single family homes program.
Yes.
Phius, if you, this gets into the weeds a little bit, but of the 3 paths for Energy Star multifamily compliance, there's a prescriptive path, there's an ASHRAE 90.1 path, and there's an energy rating index path. The prescriptive and the ASHRAE 90.1 path require review by a multifamily review organization, or what's called an MRO. There is a pathway through the EPA Energy Star multifamily program that allows you to skip the ASHRAE 90.1 modeling if you're meeting the source energy targets through Phius WUFI modeling. Okay, and for Phius 2021. If you're beating the source energy targets by 10%, you can eliminate the ASHRAE 90.1 modelings, which essentially eliminates duplicitous modeling for the project. Phius has now been approved as an MRO to streamline the process a little bit. So if you're going for Phius certification and you need an MRO and you're pursuing the ASHRAE 90.1 path, you can basically get your MRO review done by Phius as part of the pre-cert process. Okay, we're not ready to take on projects yet, but look for that to happen probably 3rd or 4th quarter this year. Okay, so that's just some happy news that we got from the EPA this week.
That's great. Thanks, Tony. Anyone else? I do have Bill Shedid, I hope I said that right, who is an AeroBarrier representative. So Bill, I saw your message in the chat, and happy to connect to have you speak at a future event as well. So maybe our next meeting will be focused on air barrier with some information on AeroBarrier technology and other approaches. But yeah, feel free to introduce yourself for a moment. We have a couple more people on the call, and I think after that we'll wrap it up.
Thanks, Michelle. Hi, I'm Bill Shadid. I lead marketing for AeroBarrier for the company, for the manufacturer. And I was happy to, I think I came across this because one of our installers, dealers, was going to be presenting. Unfortunately, that didn't happen today. So just wanted to say hi. I'm happy to facilitate, you know, at a future meeting, if it makes sense for you guys, to have one or two of our people on the call and be able to talk about AeroBarrier. We get used on a lot of passive house projects. Essentially, what we do is we make air sealing building envelopes quite a bit easier and eliminate the need for manual sealing through an automated computer-controlled system that essentially uses spray nozzles throughout the building or throughout the living unit, and pressurizes the space using a blower door, and then seals down to however airtight you would like it to get, down to even something far lower than a Phius requirement. So we've been used across the country, across the Canada, Saudi Arabia, quite a bit, and would love to share information if that makes sense for your group in the future.
Yeah, that's great. I did send you my email address in the chat, so you have it.
Gotcha. I got it. Great.
Great. Let's be in touch. And I think with that, I would just want to thank all of you for taking the time to join us and for helping to make this community so robust, and keep up the good work. Thanks, everyone.